Hey, this is Dinesh here. Today I'm going to give a brief status update on my Riscduino chip, which got taped out in eFabless CI-0622Q. Hey, I am not the new guy in the open source 130 nanometer tape outs. I have been actively working in MPW projects from 2020 onward. I have placed around 17 MPW projects, and all these white colors are the recipe based projects, and these yellow colors are non-recipe based reports. And if you see some of the places I have multiple recipe based reports. They are with the different variants. Some are with single core, some are with dual core and quad core. I have done a two sponsored tape out in 06 2022 and 0323. I have received a silicon for MPW2, MPW3 and CI-0622. Today my all discussions are related to 0622. My original vision is to see whether I can create a commercially viable SoC solution using open source environment available across different domains, such as open source development platform through Arduino and open source CPU architecture from Riscduino, and using the open source VLSI toolset from OpenRoad, and using a open source PDK, which is the Skywater 130 nanometer. My vision is to see whether I can create a SoC which can work flawlessly with an Arduino IDE, so that I can reuse the most of the already available Arduino ecosystem. Let me give a brief architectural overview. This chip has a 2 RISC-V 32-bit RISC-V core and 2 kbf an instruction cache and a data cache, and 2 kbf a tightly coupled memory. Apart from this, it has a different peripheral like a quad SPI and two UARTs and one I2C master and one USB 1.1 host and one simple SPI. But from this, it has a general purpose functions like a GPIO and 6 PWM and 3 timer and 4 LED driver. Whole chip can be configured through the three ways. One is through the Caravelle wishbone or external UART master or an SPI master. Let me give a quick overview on the Riscduino series here. Total I am driving a three chiplets here. First one is with a single core version, second one with the two core version, and third with a quad core version. The major difference between a quad core version compared to the single and the dual core is the quad core doesn't have a AES and FU IPs. That is basically the space whatever available is used up by these two cores. Otherwise, rest of the IPs are nearly same. Let me give a brief overview on the how I mapped the Riscduino SoC pins against Atmega pins. And if you see for to map it Atmega, we need 24 functional pins. And these yellow colors one are the Atmega ports, which is telling the port C6, the port D0 to D7, port B6. So these are the actual port numberings as per the Atmega chip. And these are the additional functions what Atmega supports it. And these numbers 0, 1, 2, 3 are correspond to the Arduino numbers. And these are additional functions available in the same pin. And you see this white color one is the where I mapped the Caravelle pads into the corresponding Atmega ports. Now I'm started from D5 to D7. Even though this currently I'm not supporting unlock, I made sure that the whichever digital I picked, which has a feature which supports the unlock also. So that feature when I integrate ADC, I should be able to use the same pin mapping. From the top level view, as we see how the 38 pins of Caravelle is got distributed. We can say it is split into three sections. One is specific to the Caravelle, and rest 24 signals are used by the Arduino interface, and rest of the signals are used by the Riscduino for his serial SRAM and flash for program memory and data memory. To integrate an SoC into the Arduino IDE platform, we need four contents. One is the firmware. This is basically to map all the higher level subroutine into SoC specific action. Second one is the compiler, which is basically based on the CPU architecture we have picked. Third one is the download tool, which basically needed by the Arduino to download the compiled hex file into the SoC. The fourth one is the JSON file, which indicates all the above contents in a structured way so that Arduino understands it and installs it. Let us see a demo on how to integrate a Riscduino into Arduino IDE. Here is my current debug setup. Left side I am just showing the 64 pin QFN chip, and whatever functionality I required for the Riscduino I kept it in the breadboard. Basically I need a serial SRAM and a serial flash. Apart from this I need an UART, and I am using an FTDA chip here. I am creating two new boards, one with placing a Caravelle adapter, and second board with directly soldering the chip into the board. And I am trying to make sure that the board sizes are similar to the Arduino footprint. Currently these boards are showing some issues, and the debug in progress. Current demo is with this debug setup. I have opened the Arduino IDE. Typically once you open it, to select the board, we go to tools board and select the desired Arduino board. I'm just selected Arduino Uno here, and typically when you go and try to compile it, and typically you will notice that tool uses the AVR GCC to compile it. Now let us try to integrate Riscduino into it. So we'll add our JSON file into the preference. So Arduino download that JSON file. Then we have to come to the board manager and search for Riscduino. So you can click on the install. It is successfully installed it. Now let us come and search in the board. Now you see there is an additional board. Riscduino board has come, and there is a selection for a Riscduino Uno. Let us select the Riscduino Uno. Now let us try to compile this code. I done the compile, and if you see it here, now it uses the Riscv64 compiler to compile it, and it successfully completed the hex file generation. Let me connect to the board and let us download the hex file. The hex file is successfully uploaded. Let us check the code. What is this C application is doing? It basically reads a character from the user and try to analyze what type of character it is. So if you send a character, it checks whether it's an ASCII value, or is it an alphanumeric, or is it an alphabetic, or is it an ASCII, white space, control character, numerical digit, or is it a printable, or lowercase. So all such analysis do on each character what user types it. So let me open the serial port and see how system behaves. So let me type a character A. So it is saying it is an ASCII value 65, it is a alphanumeric and it is alphabetic ASCII and it is a valid hex value. Let me value write as G. So it says what is the ASCII value, and it says it is not a hex value. Let me type as 0. It's saying its value is 45, 48 and it is a valid hex value. So it is doing is saying if I send a space, it is saying it is a space, it is a white space. So effectively the risk core is running and it is doing the action what I expected. Closing remark wise, I see a very stable silicon this time. I see system is running more than 24 hours without failure, which is a very good sign. And I see most of the critical features are working, which is required to demonstrate the Arduino. And in I can say it is like whatever I simulated in the RTL is matches with the silicon. I also see some silicon bugs in advanced and performance features. These are I am able to reproduce in the RTL. This may need an additional silicon fix. And also I see some hold issue above 1.68. I feel most of the timing signups are updated post this tapeout. I am looking for a better result in my MPW7 and MPW8 and CI-0323. Let me just share where are the Riscduino resources are available. The SOC design related data are available in the following Git repo. This is a single core version. This is the dual core version. This is a quad core version. The Arduino firmware is available in this Git repo, and tools are available in this Git repo. Bring up documents are available in this Git repo, and board related documents are available in this Git. Lastly, I like to thank eFabulous, Open Road, and Google and other open source community for supporting this low cost silicon development initiatives.